Okay, so hello everyone. Thank you for coming today. My name is Jesse. I am the Vice President for the PGSA. Today I'm going to be giving a not so brief presentation on object-oriented programming in Python. And I'm trying to put an emphasis on for scientists. When I say for scientists, I'm simply referring to the fact that I'm not going to be focusing far too heavily on the very intense nitty-gritty formalities of coding. That being said, I will be trying to maintain a certain level of formalism because I want you to have a strong enough background leaving this presentation with the terminology and practices so that when you are trying these things out for yourself and you're doing your Google searches that you will inevitably be doing, you'll be able to at least understand what you come across. For this workshop, there is a certain understanding level of Python which is going to be assumed. I also have a couple example files to share, which I'll just put into the chat at the end of the workshop. And if you need be, like if you can't make it to the end, you can just send me an email and I'll send them to you directly as well. So I am happy to take questions at any point during the presentation because I know that this is an extremely sometimes complex topic. And if you aren't following with one slide, the next slide might just make it way worse. So feel free to interrupt or put something in the chat. Evan, feel free to interrupt me if I missed a question in the chat, if you see it, or if you have a question yourself. But I do actually have a second laptop here to hopefully mitigate that possibility. So without further ado, let's move on and get started. We'll start off with the background and information. This is a sort of theory portion of the workshop, and it won't touch directly on Python. Overall, there are two different types of programming paradigms, as they're called. I've chosen to actually loop two of them into one. Some say that there are three, but the difference between the first two are not necessarily too drastic, at least to a scientist's eye who's not being very complex. The first form is functional programming, where oftentimes your repeated code is going to just be broken up into functions and called in a very specific order that you would like. Oftentimes in this functional form of programming, you'll be handing in your data and your parameters constantly from one function to the next function, returning anything, giving it everything that it needs, and accepting what it returns back. Because you are accepting something back from this function, it's not really an in-place operation. You are creating new data from the old one rather than replacing the old data with new things. This is very common in functional programming. It can be done differently. You can, for example, overwrite NumPy arrays on the spot. However, in a functional programming approach, these sorts of things are avoided, and you tend to always want to return something new. The second paradigm is object-oriented programming, where you'll be trying very hard to encapsulate as much of the relevant code inside one single class. In this situation, rather than having to constantly hand the data and the parameters to each function, the data and the parameters will remain within the scope of the functions that are in the class, which are called methods. In this situation, in-place changes are actually extremely common, as you'll see when we start giving some example classes that are already in Python. So why might you want to learn object-oriented programming? Despite what you hear from any of your developer friends or object-oriented preferring friends in science, it is far from some holy ideal. It is nothing more than a style of coding which fits some people's preference. Preference means it is extremely biased. You will likely find that there are things which are definitely overkill, so please listen carefully for Professor Oak in your head, telling you when it's probably not the right time and place to be using something this complicated. That being said, moving forward from this workshop, it's obviously going to be best if you can try and find situations where you can take a script that you already have and see if you can try it again in an object-oriented approach, even if it is necessarily a bit overkill for it, just because you'll want to get some practice, as a lot of these sorts of styles are very developed and learned through Googling and trying out new things. Overall, object-oriented programming is another tool in your belt. As your projects will grow, you'll find that it could trivialize some of the problems that you face. And what I believe is really key is that it's pretty much everywhere in scientific coding, even when you're not realizing it. A lot of the Python types like dictionaries, sets, lists, they are technically classes, be it whether you knew that or not. NumPy arrays, the interpolation tools that you'll see in things like SciPy. They're optimizers, matplotlib's plotting library, and APIs that you interact with if you use any sort of electromagnetic solvers that interact with Python. So things like MEEP, the open source FDTD, or Lumerical, if you have money. When you understand more of what's going on behind the scenes, the things which are capable of doing with these classes limitlessly increase. Under the right condition, object-oriented programming can drastically improve several factors, from your readability, because your classes can be inherently more organized, your shareability, because it's very oriented towards creating a final product or tool that can just be shared and hand to somebody without them having to necessarily look inside it, and the generality, because the focus when you're developing these sorts of scripts is something there you can easily swap their purpose thanks to some of the features of object-oriented programming. But it can also get extremely messy and confusing for untrained people to work with. And if your objects are far too niche, then they aren't general and these things start to fall apart. So how can you know when you might want to go for this form of paradigm? To understand that sort of a thing, you will need to look at what are called the 4 pillars of object-oriented programming. The 4 pillars begin with encapsulation. Broadly speaking, this refers to self-containment. All of the required variables and functions which are needed by a class will be nicely self-contained within it. You will never have to worry about having to give them what they need because they already see it. So for a visualization of this, I am going to show an empty Python class with no actual real code in it. Don't need to worry about understanding what's in it. I just want to show you that, switching to the laser pointer, the functions which your Fourier data set will interact with are things like reading in its data, plotting its data, performing integration. You'll never have to worry about defining that function in any script where you're using this Fourier data class because it'll be nicely integrated within it and it'll have access to the data. The next pillar is called abstraction. And broadly speaking, this is an ease of use feature. There are large bouts of code in these external files that you can then import and just use for your own work without having to worry about what's inside them. This helps with the shareability of the code. As you can see, there is this plot function, which in some other code, I can know that I need to do .plot, but I don't necessarily need to know how that .plot method was created at all. This allows users to make use of very long and complicated procedures without having to really interact with them in a high level. This is great for sharing with others when they can just use the class and you know that it's robust enough to not necessarily be giving them a lot of errors. And they can use all of those methods, no idea what's going on behind the scenes. The third pillar is called polymorphism, and this speaks to the flexibility of classes and how they are interacted with. The different classes that you create can have any appearance that you would like them to, which means that they're flexible in how you will interact with them. Lots of the things need visualizing, then you can just give each of those things a plot method. So even if they behave wildly differently, it won't matter. You'll know that no matter what you're interacting with, you'll just have to do .plot because you've made it so that even though they're fundamentally different, they're interacted the same way. This actually has a lot of benefits in terms of consistency, as well as it promotes a lot more clean code, because if you think about it, this will give you the opportunity to completely ignore these situations where it's like, if this kind of data, do this plotting function. If this kind of data, do this plotting function, etc. You can eliminate all of those if statements and all those switch cases if you're using other languages, and you're set to go. The final pillar is a touch more niche to explain without already knowing classes. So this will be really brief, but essentially it touches on the ability to recycle code that you've already done. So this refers to the ability to help minimize redundancy in your code, because for example here, by having this subclass inherit the properties of this parent class, we'll talk about this in the third example, you can call this integrate function, which is something of time data, and it won't give you any errors because even though it's not there, it knows what to do. It knows what to call. So we've talked a lot about objects, but I haven't really explained what precisely they are. This may not make a lot of sense in sentence form, so after this, we will go over an example to hopefully clarify. But an object is an instance of a class, where a class is just a general framework, structure, blueprint, however you want to call it. A class has predefined attributes, which will define the object itself. So even though two objects are of the same class, their attributes are what make them different from each other. The class also has predefined methods, which are just the procedures or the routines that the object will perform. An example of this could be a person. They are a general blueprint overall, and a person will typically have generic attributes associated with them, like their name, height, age, and birth date. But when we declare the object, we fill in the blanks of this framework, giving it a sort of identity. We can then make use of these predefined methods for the object. So in the case of a person, you can have the name, the height, age, birth date, and some routines, some methods that they might have is eat, sleep, and study. Now let's move forward to objects and their presence in Python. Their presence is literally everywhere. You may not realize it, but honestly, the most obvious example would be the Python list, something that you'll learn the very, very first time you interact with Python, most likely. As you can see, there's multiple ways to declare a list. Some are the ways that you are familiar with, that you might likely learn when you are first learning Python, but there's technically alternative ways which will more likely resemble how you would define a class. So here in this little example, a class list is an object of type list, where list is the class. Classes will have their methods. So for the list, the existing methods like append will operate in place. So in this example, I have this list and I'm appending Evan to the class list. And as you can see, nothing's being returned from this append function. The class list is just simply changing. This is what I'm referring to when I say that something is happening in place. I'm obviously not going to be going over every single method of a list, as that's a very beginner Python oriented, and I'd like to move on. But NumPy arrays are actually also great examples of classes which you may frequently interact with. They have their methods like sum, min, max, and they have their attributes which you may call upon, like their real and their imaginary portions. And you may have noticed what the fundamental difference is between an attribute and a method when you're interacting with them in Python. A method will have brackets, or a call as it's referred to, and attributes, generally speaking, don't. That's not always the case, but for the most part, it will be true. So a quick aside, I just want to make sure that the terminology when referring to functions or methods is consistent. When it comes to a function or a method, it will have a name or a handle. I might switch between these two terms willy-nilly. And then there are the arguments, which are the things to be handed to the function. Ultimately, when you use the rounded brackets and you're giving them these arguments, this is called the call to the function because you're calling for it to do something for you. Let's have a first example of a class in Python and actually learn how to make a class in Python. The first example is going to be very minimal and not at all science related, just so that it follows my earliest description of what a class is. So we're going to start with this person class. It'll ultimately resemble the function declaration, but instead of having define function name or def function name, you'll have class and then the class name with the colon and then the indentation block defining the scope of that class. The very first thing that you have to do is define a method inside the, or a function, method is more precise, sorry, called __init. This is called the constructor. It's ultimately the initialization function of your class, hence it is init. The variable self is required in this function declaration. And this might sound weird, so let's talk a little bit quickly about what self is. When you define a function, a normal function, you have to give the variables that that function will be interacting with. This tells it not only what to refer to it as, but also gives it the ability to see that variable in the calculation. For a method, you'll have to do a very similar thing. You have to give it self, and that way it can actually see itself and know what to refer to itself as. So every single method within your class will require self. It's a very easy rule to follow. Just make the first argument always self. Hi there, Jesse after the fact. I was told after the workshop that my explanation of this part self wasn't necessarily as fully flushed as it could be. So I really wanted to go back to explain it because it is at least important to understand what's going on behind the scenes perhaps, and knowing why you're putting in the argument, even if it's just to know why you'll get an error if you don't put that self there. So here I've described that it's how it refers to itself because you're probably going to end up referring back to itself during your methods at some point in time. But let's talk about the errors that arise when it's excluded and what's really going on behind the scenes. So you can also view it like this. When you're calling a method, for example, the append method to a list, as we keep on referring back to, what you're seeing is this. You have your class list and you append and you give an argument of what you want to be appended. But that's not actually what's going on behind the scenes. You see, you write script, but then Python is ultimately what interprets your script. And it will then interpret your script and execute it sometimes slightly differently than how it looks. In this scenario, how it executes it is actually more resembling this line here, where you have a second argument being added in the first slot, which is itself. So here's the object class list, and here's class list just reappearing inside this method call. In secret, it's doing this, and so no matter what, you'll always need that self there as the first argument. So what happens if you exclude it, if you forget it, or you just don't need it? Well, if you do, you'll get a weird error. So here I just have the init function and I've deleted self from the front. And now when I'm calling to initialize an object of that class and I'm giving these initialization arguments, you'll see that I gave two arguments, a name and a height as specified here above, but I get an error right away. And that error says that it takes two positional arguments. It's seeing the two here, but three were given. Well, you can see in my line of code here that I never gave three arguments. So why is it saying that three were there? Well, it's saying that three were there for the exact reason that's described on the previous slide, which is that when Python actually interprets the code, it's inserting that extra argument at the beginning. So even though there were only two, Python is telling you that three were given because that's what it's doing in secret. So you always need to have a self there, even if your class isn't going to be referring back to itself at that point in time, it always requires it. Okay, back to the normal workshop. So when you're assigning attributes to your class, you just do so typically in the constructor. The constructor will take additional arguments, which will be anything that you need to initialize your class. You will assign the attributes to your class just using self dot, whatever the attribute will be named, and then equals the attribute. How would you use this new class? Well, it's as simple as you just call the class name and give it what is required to initialize it. These are the things that you have specified in your init function. You'll notice though that self is excluded. As I already said, every method to your class will have self. So it's sort of implied and doesn't necessarily, like it doesn't need to be there at all. It's redundant. To access your attributes, you just do dot and then that attribute. With the NumPy arrays, it was .real, .imag. In this case, it's .name. So you don't need to hand in every single attribute directly. So I handed in a name and then I set self.name to equal to name. But you can do things with what you've handed in and initialize a lot more than just what you handed in. Some can be determined through calculations, for example, as I have here on the right. Oops, skipped ahead a little bit there. So here I've also handed in a height and I've assumed that it's in centimeters. And then I've just created this arbitrary other attribute, which is my height in inches, and just taken the height and divided it by 2.54. Obviously, I didn't give it height in inches, but I can create an attribute height in inches. It's important that your constructor does not return anything. As we know from functions, what is being returned is what gets put into the variable. So if your init function is trying to return something, it conflicts with here where you're trying to say that you're initializing a class to put in this variable. They're both trying to put into this variable and you'll get errors. Luckily, very clear errors where it'll tell you that you've tried to return something from your init. Ideally, every attribute will be initialized within your constructor. You don't want to be creating attributes as you go in other functions. This isn't very good practice, but obviously it's not a restraint of object-oriented programming in Python, at least. This is because if you create a method which requires an attribute which was only defined in a different method and not in your constructor, and you call it accidentally out of order, you'll get errors that that attribute doesn't exist because it wasn't properly initialized at the beginning. So let's talk more about defining other methods. When it comes to defining other methods, there's no difference between defining a method and a function aside from starting it with self. You define the function or the method inside your class, just indented so that it's within the scope of the class, and you give it the very first argument of self. Here I have two examples. I've created two methods, a sleep method and an isSleeping method. Sleep will just set this sleeping attribute to true, and isSleeping will just tell me whether or not this object is sleeping. In this scenario, you'll see that I've put an underscore at the beginning of this attribute. And the quick note on this is, if you don't expect a user to be interacting with an attribute, common practice is to begin it with an underscore, and that tells the user, you shouldn't touch this. So here is this code from the previous slide actually put to work. I have here where I define a person, Freddie, named Frederick, height 186 centimeters, and I ask if they're sleeping. They begin awake, as we've set up in the initializing function, and then we put them to sleep, check again, and they're asleep. Very simple, straightforward. An important thing to note, though, is that all of your methods can actually see other methods and can be seen by each other. There's no special sort of thing that you need to take into account in this situation. So here I've created a new method study where it checks to see if they're sleeping before it tries to make them study, because you can't really study while you're asleep. So you can see that you would just call it using self dot instead of as it is previously, because that's how it will refer to itself. This is ultimately the pillar of encapsulation showing, where everything that it needs to see is nicely wrapped within itself. So if you'd like to mess around with this or take it even further, I do have an example one file. I will be posting all these files at the end of the workshop. If you don't make it to the end, you can send me an email. I already said that, but I did notice that some people left and new people came. So I'm just going to say that again. It is the exact class code that I've shown on these slides and follows by just a brief bit of code with the sleeping interaction. I have a couple little homeworks for you with as punny names as I could possibly think of. But I would just like you to try and do these on your own time if you're feeling like taking object-oriented programming a little bit further and getting some practice with it. This first one is as similar to the person example as I could think of. It's just a dog instead. I just want to make sure that you can initialize your classes, set your attributes, and create a method. Before I move onward from this exact point, I do want to pause to ask for questions, because that's the basics of defining a class and interacting with the class, and not any of the more complicated things. But we're about to move into some of those more complicated things. So if you're having trouble following up until now, it might be a little bit difficult to keep moving forward. So if there are any questions, speak now or forever hold your peace. Okay, let's keep moving then. Good, it was a simple enough example. So our second example, we're going to create a class for a pulse. This is going to be just slowly inching towards a more scientific approach. In this scenario, we're going to make use of important kinds of methods, which are called magic methods. They do have other names which you might stumble across. I'm not really familiar with them because I learned their name magic methods and I stuck with it because I like the name. So our starting point for this example will be what I have on the slide here. And obviously this code will also be included. Here I've just created a class and the constructor takes in an amplitude, duration, and wavelength and stores those in slightly differently named attributes to the class. As well, I just calculate some extra things that it'll need for what we're about to be doing. This example will require NumPy, and later on we'll do some plotting, which means it'll also require matplotlib. And I've created a global variable constant at the tops. Because it's outside the scope of this class, it's considered global. It's outside, it's in a greater scope than this class, and thus the class can see it. So your magic methods, ultimately in Python, these are what is going on behind the scenes, controlling how your functions will work on the different objects. For example, the length function will work on both lists and NumPy arrays. Why is that the case? Not only how they behave inside functions, but also if they were to be called as if it were a function using the rounded brackets. There are so many things in Python that are using these magic methods, and ultimately they're functionally equivalent. So here I have the same class list from earlier where I call the length function on it. But here I'm showing that there's actually this method that we don't really see ever, which is __len, which does the exact same thing. So all this length function is doing is calling this method. So if you define these methods for your classes, you get to control how they behave with when they're treated like functions, or with being used inside other functions, or being used with operators like logical comparisons or mathematical steps. This is an extremely abridged table of some of the magic methods because ultimately they go on for pages. But for example, when something's being converted to a string or an integer, it's just calling __string or int, etc. And that's what the print function is doing. If you're giving square brackets, like an index in a list or a NumPy array, that's just the getItem method. Rounded brackets is the call method, len I already showed to be len, and then your plus minus mathematical operators are add and subtract, etc., div, mul. And you have the similar ones as well for logical operators like and or. So let's add a call method to our pulse so that we can use it like it's a function for our pulse. Here I've added this call method. This is what it would look like. Just imagine it inside the class. I'm obviously not going to be putting the whole code every single time. It takes in one argument, which is t, and then just returns a Gaussian pulse at that time t, assuming that the duration that you give was the full width half maximum of the Gaussian pulse. Now, when we initialize our object of class pulse, we can actually just call it just like it was a function and gain our values. So here, just like the person class, I create an object in the signal variable, which is of class pulse, give it the initialization parameters, and then now I can actually just evaluate a bunch of pulse points by handing it some time points to evaluate at, as if it were a function. You might recognize this sort of structure in some other things that you've interacted with. Like for example, SciPy's interpolation functions work this exact same way, where you're actually defining a function and then calling it. Well, it's actually a class which has a call method, which is doing the interpolation for you at that exact value. But you also could have just done that with a function and some global variables. It's not necessarily that magical. So if that was all you needed, you probably wouldn't want to be using object-oriented programming for this. So let's continue with this example and make it a touch more complex to suit something that we might be interacting with. The ultimate goal is not having to rewrite any pulse code after making this class once, something which is usable across several cases. And a good thing with your pulses is you're probably going to want to be able to see what the pulse that you are using in many cases. So let's create something to visualize that pulse. Here I've just added a simple plot method, and I've used a keyword argument so that you can control optionally the number of points in which you will be plotting. This works generally for any duration and the Gaussian pulse that we've defined earlier. And as you can see, you can call it using self and the rounded brackets as well. Now you can plot your signal as easily as just signal.plot. But why would you spend the time to create this one general plot function for this pulse? Well, now you have something that you can save to a separate file and use freely in any of your scripts. Once it's done, it is done. You can import it and use it whenever you would like to and avoid possible issues. So here I've just saved pulse into a file pulse.py. So I'm just importing pulse from that file, and I'm creating two different pulses with different parameters. So let's compare this to the functional approach to show where exactly these benefits are coming from. When it comes to the functional declaration of this pulse, you will always need to give it the amplitude, duration, and wavelength every time you're trying to evaluate that pulse. The option to get around this would be to use global variables, but this can lead to you having issues when you're having more than one pulse at a time. If you want to get around those issues, you'll likely be breaking some practices like adjusting your global variables in runtime. And when it comes to the visualization approach, you'll see that it starts off with a lot of the exact same problems. You have to always give it the amplitude, duration, and wavelength. And if you're specifying it multiple times throughout your code, you're actually increasing your possibility to make errors. If you've accidentally changed the variable that's going to be headed into the function, or you just accidentally don't put quite the right variable into that function, you could have simulation code which works perfectly fine, but then all of your visualizations don't look right, and you'll not necessarily know why, and you'll have to waste a lot of time because you didn't have that guarantee that what's being used in your simulation and what you are looking at are definitely the same. Here as well, you've lost your polymorphism aspect. You have a nice dot plot consistency between this pulse and any other class that you may want to work with in the future. And then you'll start needing to create names for unique functions with unique names for each of those visualizations. So visualize pulse, visualize DFT, etc., rather than just a simple dot plot across any code. So this leads into the second homework, where I want you to start with the pulse class and add a DFT method for this. As well, I want you to use the magic method, the string method, which will be used inside a print function, just to have it return the amplitude, the duration, and the wavelength in a nice sentence, however you would like it to be worded. The third example that I'm going to go through is just a subclass, and this is going to look specifically at this inheritance property that we talked about as one of the pillars. So with subclasses, it's pretty much solely the inheritance pillar, and it allows you to avoid a lot of repeated code. But most importantly, and my favorite, is it lets you take the best of other people's code or something that you've already written yourself and just adjust it slightly in order to make it best suit what you need. So a subclass looks identical to a class with as little as one difference in its declaration, which you might be able to tell is just this bracket where I'm stating what the parent class is. So this is just telling Python to inherit every single method that we have defined from Pulse and put it inside costPulse. A plot, length, call, get item, anything except for the initializer. But though that constructor is initially excluded, if it is the same constructor for both classes, you can also recycle the initialization function. You just have to put this slightly ugly block of code at the very beginning. So when it comes to a subclass, you can steal from virtually any class. Python lists, NumPy arrays, you go for it. Anything that will make your life easier if there's something that you can take from. I used to steal a lot from Python dictionaries so that I could, instead of use the dot attribute notation, use the square brackets and a string key. Let's make our first subclass using our Pulse class and just change the envelope that it uses. In this scenario, we have the same initialization function, so we'll just use that super init that we've talked about. And by default, everything is the same. But if you don't want to use something that already exists within that class, you have two ways to get around this. The first way, we're not going to talk about because it's a little bit weird. But the second way is just redefining that function. If you redefine it, then it will just call the one that it's been given fresher rather than the one that it inherited. So here you see all we need to do is replace our call function because our Gaussian envelope was just inside that call and the plot function used that call to make the plot. So we only have to replace one thing. So now I've taken this costPulse, which is a subclass of Pulse, and I've just changed that one call function and added in one thing that the raised cosine pulse needs. And now I can declare a cosine pulse signal and plot it as easily as dot plot, even though there was no dot plot method created in our new class. And this is the third homework, which is just creating a subclass of Pulse from homework 2. You can create any sort of subclass that you would like, but I would like you to create a new method for visualizing it in both the time and the frequency domain profile, which is why you would need to use your subclass from the second example problem. Overall, that's actually it for subclasses, which is why we're moving on. They're really not that complex. The real emphasis is just recycling your code and making your life easier by borrowing other people's hard work. So where might object-oriented programming be useful in science? We're done talking about the tutorial portion because that was pretty much it. You've now learned how to declare an object, how to use magic methods, and how to use subclasses. And the rest is really just practicing those three things and finding situations where it might be useful in your work. But that's kind of the elementary school question, which is where are the real world applications for this? Well, that's a really loaded question overall. So let's discuss this by first starting off the bat saying, when would you not want to use object-oriented programming? Well, the things that wouldn't benefit are very small, fast, and trivial things. If somebody hands you some data to look at just one time, you do not want to be spending all that time making a whole class just to view it and interact with it, unless you're going to be looking at that sort of data constantly. Overall, a big common theme for cases where you're not going to want to use this is anything which isn't going to be revisited or reused, because it'll just add time and complexity. When it comes to classes which are going to be used very frequently, you spend the time on it once, and then you'll never have to spend that time on it again. So the time that you spend making the class is valuable. But the other way around, if you're not spending that time constantly revisiting it, then you're not really saving anything in the long run. And an object-oriented approach is a very bad idea. Things which you might find object-oriented programming useful for is the creation of different custom tools or wrappers for things which are of frequent use to you. For example, if you have a very specific output data type from your lab equipment, or you use a lot of external data sources that you are constantly importing from or using an API to interact with, then these are things which are really useful for object-oriented approaches. These things are often found in simulation and analysis. And since object-oriented programming is usually approached with the goal of as much generality as possible, you often get something that is very long-lasting and can easily be updated for new purposes, as all you'll really have to do is create one new method, and you can already guarantee that all the variables and attributes which it has will automatically be visible. You'll never have to worry about whether or not your function's in the right spot or will have access to all the right data. So here are some just custom or unique tools that might use an object-oriented approach. For example, you have interpolation, as was already shown with SciPy's interpolator function. And you have pulses, which we've talked about, which is great for simulation approaches. But something that I would like to really emphasize is the data manipulators aspect. And the reason why is when it comes to classes, you can use the attributes to serve as metadata for the data that you're working with. As well, because Python has a lot of great friendliness with their pickling and their classes, you can actually take your classes and pickle them in an instant and load them back up, which means you won't have to worry about recalculations or reinitializing. When I run my simulations, I can output my simulation classes into a pickle and then just reload them in an instant without having to wait for them to rerun. Here as well, you can establish different routines on how it will interact with other data or how to filter and use your data using these methods. So this is actually a very abridged piece of code that I made in 2 days and then used for 8 months at one of my jobs. The reason why is I spent the time to create all of this generality, but then I realized there was a lot of functions that I would need. So removing specific time series data, because this was satellite data measurements over a long period of time, about 16 years. And there was lots of functions that I needed to define, so like how it would interact with other data sets. And there was lots of analysis that I would be frequently revisiting on the spot, like if I needed to average by year or month, etc. And so I created methods for all of these, and then 8 months worth of analysis was used in this one class. And when I walked away, all I had to do was give a brief instructional document to somebody saying, this is how you use each method, and then they were set to go and they could use them to continue on my work as I left. Simulation work benefits a lot, as you might have guessed. Things like FDTD solvers, MEEP, Numerical, they've used these object-oriented approaches, as I've already said. They work very well as managers for very large tasks with lots of complicated interdependencies, as they can actually manage those interdependencies very well. You can run multiple simulations in parallel without having to worry about competing variable names. For example, if you have to define multiple electric fields and trying to figure out what each field will be, it'll just be way cleaner if all of those fields are nice and encapsulated within their classes and you don't need to interact with them. This makes your code really readable overall. When you create one simple simulation class, you have infinite simulation data because you can just change what your parameters are, rerun simulations on the go. One working simulation class could do months of different analysis work involving varying simulations. As well, there's preference to in-place operations and object-oriented approaches, which can actually help with your memory resource requirements of these situations because you will not be as often duplicating objects just to replace the old one, where temporarily you've doubled your memory requirement for that specific object. Ultimately, it's a lot of very clean simulation code since it's all in one file, and you can just run 5 simulations in a couple lines of your actual experimental or analysis code. This is something which I am currently doing, where here I've created an FDTD solver in one dimension, and I can perform an entire simulation and analysis on the right with just these few lines of code. So this is definitely an approach which I would push for. Moving forward is anything where you're performing any sort of calculations involving standard electromagnetic things in your work, I'm assuming as physicists. This is an approach that you might want to start pushing toward if you will be reusing the simulation code a lot. And that actually takes to the very final homework assignment, which is just to build a random number generator of your own. You can use whatever method that you would like, but I would recommend a linear congruential generator just because I have given that example to you. I have it in the files which I'm about to attach. I would like you to add a method like uniform. This uniform method should look like the NumPy uniform random, where it's going to give you a random float number from a uniform distribution from 0 to 1. And then create a script which will use this random number generator to pick an item from any number of items in a list. And that should, if you are capable of doing this, then you are capable of finding classes and integrating them into your different analysis work or to solve certain problems. And that is actually all for the presentation, taking only 40 minutes, which is quite surprising. I will stop the recording and open the floor up to any questions from here on out. But I would like to thank you for coming, and I hope that you can take the example files that I'm about to attach and move forward and gain some intuition for object-oriented approaches where they're applicable.